Okay. Live.
Yay.
We did it.
Excellent.
Oh, I got to open up a new Audacity window. Okay. All right. Mandatory launch hold. So we've got all your questions. Our good friends from the Weekly Space Hangout crew moved over a bunch of your questions over into the chat, so we'll be able to tackle that. Or we could just talk about Starship. Whichever people want to do. It took more than a second. Yes, it took more than a second. Just save onto the old track in Audacity. Yeah, just overwrite it.
No. We've done that before by accident. I've done that before by accident.
Oh. Yeah, it's funny. Like, I think when you make a podcast, you make a bunch of those horrible, horrible mistakes early on. Yeah. Oh.
Yeah. Well, and we made that mistake not only early on, because that's just human error.
Yeah, but we've been, I mean, for the 540-ish episodes that we've done, for the number of times things have gotten totally destroyed is very low. There's been a couple of cases where Susie has had to recreate the episode thanks to the YouTube audio as a backup. Yeah. So that's happened. And that's kind of great. That's one of the real advantages to doing these things live is that we are able to, we have that backup. And so it's, it sounds like garbage, but at least it's better than...
We have it.
We have it. Yeah, exactly. Were you on with Skeptoid?
Yes. And since when have you thought that there wasn't life in the universe?
Always. Have we not had this argument yet?
But you always talk about how you want life to be found in our lifetime, and I say I don't want that to happen.
No, yeah, I want to find it. I don't think it's there, but I want to find it. You just don't even want to find it, you monster.
That's true. I want to find it far, far away.
Yeah.
And not while I'm alive necessarily. Yeah. I'm good with like finding plants.
Yeah.
It's the intelligence. I'm not sure what society is messed up already.
People, you know what? Society has demonstrated its ability to become bored of anything.
That is true as
well. That's my position.
That is true as well.
That
is a good point.
Yeah. Right? So that's all. That's literally, you think people are going to freak out and it's going to be pandemonium all the time. I think people are going to be like, I don't care. And then they're just going to go back and
prior to 2016, I would have argued with you, but no, you won that one.
I win.
Yeah. Okay. So, that's fair. Yeah. That's fair.
Yeah. But no, the Fermi paradox freaks me out. So I think, and so that's why I'm like, I can't think of a reason why we shouldn't have aliens everywhere. And so therefore.
Okay.
All right. Where were we? What are we? Who are we? What are we doing? What is this?
Age of the universe and whether or not it's older than stars.
All right. You know what? It's time to say hello again, just for fun. I'm going to say hi to Adam Synergy, Andy Cowley, Anti-Gravity Nonsense, Beatrix Lidner, Ben Kalo, Bill Sugden, Chai Latte Nebula, Cherry Cat Naps, Colin Jones, Dustin King, Dusty Reichwin, Frank Tippin, Gordon Dewis, Janelle Duncan, John Drake, John Seffield, Kara H, Quadlibet, Linda Sadiq, Michael Bommet, Nancy Graziano, Paul Disney, Paul Gracie, Raj Luthra, Arjone, Sean Kenny, Sergusi, Susie Murph, Therian, Time of Dying, 00, Uncle Bill Druin, William Vandebeek, Yamagashi-san, Yuvil Litvin, and Zapfan. Hey, everybody. We made it to this this part 2, but it really, they're so intertwined. I'm surprised that it even turned into its own separate episode.
Well,
but it's such a big topic.
I knew we needed the full.
Yeah.
And both of them have really cool histories.
Yeah, so we'll approach the age part now from a different perspective. It's going to be fun. Okay, well, if everybody's ready, so we will do this, and then, we'll be wrapped up sometime after 1:15 or so, and then we'll stick around.
Yeah.
How's your time? Like, stick around for like...
It's pretty tight.
Okay.
I have a telecon at 2 Pacific, and I have not had lunch, and I don't want to like eat people during my telecon.
Okay. All right. Well, then we will probably have to shut it down pretty quick as soon as we finish.
Okay.
All right. Let me know when you're ready, and I will press record.
I press record.
I've also pressed record. Here we go. And I know I've got the right title this time. Astronomy Cast, episode 540. Astronomy Cast, episode 542, Weird Issues, the Age of the Universe. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser, Cain, publisher of Universe Today, and with me, as always, Dr. Pamela Gay, a senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing?
I'm doing great. Again, this is like a two-part episode. We're actually recording them at the same time. You are at the Planetary Science Institute, working for the Planetary Science Institute, near all of the planetary science that gets done in Tucson, Arizona. How are you enjoying your time there?
It is remarkably hot.
In October?
It is.
Yeah.
And there are little lizards everywhere.
Aww.
So if you wish to be in the land of heat and little tiny lizards, I recommend Tucson, Arizona. But it's been great getting to collaborate with everyone, see everyone face to face. I am not here long enough. There's so much interesting work to do, but we're at least getting the face-to-face few moments to start to plan out what will happen in the coming months.
Yeah, it's a beautiful landscape, and those desert skies, if you can get a chance to get out and see them. Our series on universe weirdness continues, and this time we learn how astronomers are struggling to make sense of the age of the universe. All right, Pamela, now we have absolutely covered this topic several times in the past, I'm sure. How old is the universe? And I feel like last time we talked about this, we were a lot more definitive than we are today.
This is why we are revisiting the subject.
Exactly. Turns out things are more complicated than we thought.
And this has always been true with trying to figure out the age of the universe, whether you look back in history at the people who tried to figure it out from generations of begats to the scientists who tried to figure it out by looking at the total mass of the sun and figuring out how many years it could burn for given the current energy output, to, well, once we figured out nuclear reactions, we started figuring out stellar evolution and figuring out, well, how long should stars be able to live and what are the oldest stars that we see? And then finally, with the expansion rate, you can run that sucker backwards and figure out when our massive universe would have completely collapsed in on itself and get an age from that.
And astronomers did the best they could using that. And so did they get a number?
Well, we've gotten lots of numbers.
Right, but that was like one of the first ones, right? Which was like, oh, stars should collapse. How long is that going to take? And the answer is like a million, a couple of million.
Well, so what's been lovely to watch is it started out with at about the same time that we figured out plate tectonics might need to be a thing. They also figured out that the sun needed nuclear reactions because without them, it would only live for like under 10,000 years, which is not enough time. Early stellar models looked at globular clusters and ended up with globular clusters being 15, 16 billion years old. We had quite a number of difficulties for a while because that tells us the universe has to be more than 15 or 16 billion years old, because stars shouldn't be able to exist in a universe that is younger than they are. That's just a fundamental truth, we hope. And then with the expansion rate, when we didn't know the expansion rate, we were able to get a universe that was quite short-lived in the billions instead of the tens of billions of years if you just crank that Hubble constant up into the hundreds, which is where it was temporarily.
So I want to just return to those ideas for a second there. So with the globular clusters, right, you know, we know that all the stars in a globular cluster formed around the same time. And so astronomers literally just look for the oldest stars they can find. And that tells you, like, and so if you find 13 billion year old stars or 14 billion year old stars, therefore the universe has got to be older than that age because all of the young ones have all died.
And we try and make it even simpler than that. Stars go through a variety of different phases in their evolution, and the first and longest phase for the majority of stars is a hydrogen burning phase deep in their core. This is the main sequence part that stars like our own sun and most other stars go through. Some of the bigger ones have a slightly different process. We're going to ignore them. When we look at a globular cluster, we can look to see what are the most massive stars that are still undergoing hydrogen burning in their core. And the physics isn't that terribly complicated conceptually. It's always in the details that things get messy. It isn't that terribly difficult to figure out, okay, so you have hydrogen burning going on. We can figure out bits and pieces of how much mixing might be occurring and how long can these stars possibly burn hydrogen before they have to evolve to that next step because they're out of hydrogen in their cores.
Right.
And even with that much simplified version of only having to figure out, well, how long have things been around that have run out of hydrogen? We were still running into problems of globular clusters could be like 15 billion years old or more.
Right. But like the analogy is like you talk to a school and you find out, you know, what reunions are coming up for that school. And so you're going to have the 35th reunion, you're going to have the 25th reunion, you're going to have the 15th reunion. But if the school was only created 50 years ago, you're not going to have the 55th reunion. Right.
Exactly.
And so you can tell, you can just sense how old that school is, and therefore you can tell how old that globular cluster is. So that's the one way. Great. At least that gets you to within the, you know, to the nearest 10 billion years.
Yeah.
But the other method, and this one seems to make sense, right, is that if we look out in all directions and we see these stars and these galaxies moving away from us, run the clock backward, we should be able to calculate when they were all together, smushed into a region of density that, you know, would tell us that was probably the beginning of the universe.
And just to state something that we've stated so many times before, they didn't all smush down into the center of the universe. There is no center.
Did you hear?
To the universe.
I even was very careful. Did you hear I said that?
I know. You were so good.
I know.
And so here what we're looking at is if every 1 megaparsec of space, as we talked about in the last episode, is expanding by somewhere between 65 and 75 kilometers per second, well, you can take that 1 megaparsec of space and figure out when it was the size of an atom. And that is quite simply how we get at the age of the universe.
Yeah, the way I sort of have come to describe this is that you imagine the universe today as this grid, like a three-dimensional grid that goes on in all directions forever, and maybe forever. And so over time, the squares, the cubes in that grid are getting bigger. They're getting less dense. And so you could run that clock backwards all the way back to the beginning. Now, it might still have been a series of, you know, cubes, you know, this grid that goes on forever. It's just that it was way denser in the past than it is today. But it might have been infinite back at the beginning. But what we're wondering is, at what point were the gaps in that grid, you know, from what are today, as you say, you know, millions of light years apart, at what point were they all essentially really tightly packed together?
How many times can you put the graph paper on the reduced setting on the Xerox machine?
Yeah, exactly. And so that feels like a relatively straightforward Newtonian physics question. You know, you
Right.
calculate, you know, the velocity, you know, the time that tells you. That tells you you know, it tells you you know the distance, you know the velocity, that tells you the time.
Right. And where it gets messy is if the expansion rate is a constant, you just math it. It's the age is equal to 1 over the expansion rate. But if that expansion rate isn't constant, you now have to start figuring out how is it not constant? What factors are making it not constant? And this is where it gets really ugly, because we start having to take into consideration the changing mass density of the universe. We have to start taking into consideration also the geometry of the universe. That has always been a concern you have to figure out, because if the geometry isn't flat, everything goes slightly sideways. And looking at all of this, we were able to get, even with the accelerating universe, a universe that appeared to be 13.8 billion years old, and stellar evolution was giving us globular clusters that were 11 to 12 billion years old. All good so far.
Mm-hmm.
We can also, another way we can judge the age of the universe is you look around for cold white dwarf stars. And we think roughly how long it takes a star to evolve all the way from being a main sequence star like our sun to becoming a red giant and doing the red giant thing all over the HR diagram, to puffing off its outer atmosphere and leaving behind that hot core that we call a white dwarf star. And over time, that hot core, because it's not generating any of its own energy, it's just going to radiate heat into space and cool off. By looking for the coolest white dwarfs we can find, that also gives us a limit on the age of the universe. And we're back to the point of, for a while, it looked like the stars were all older than the universe.
Right. But and then there's this gift that the farthest thing we can see in all directions, the cosmic microwave background radiation, is redshifted, right? And you can essentially calculate how, you know what color that light should have been when it was originally released. You look at the color that it is today, again, relatively straightforward math to calculate how long it has been expanding to help you. And that's how we got the most accurate measurements of all, thanks to Planck.
Right. And it was more complicated than just looking at the temperature, but all of these things should give us one age.
Yes, please.
Or at least all of the stars should be younger than those Planck ages. And this is where things are currently verklempt, for lack of a better word.
They got weird.
They went sideways. When we look at the expansion rate of the universe, we're still getting like 13 point something-ish, close rounds to 14. But when we look at our lambda cold dark matter models and we use the cosmic microwave background measurements from Planck, and also when we use models that we didn't quite get to in the last episode, where we're looking at gravitationally lensed images of distant quasars, it's another way to get at distances across the universe. This starts to get us to a younger universe that has a faster expansion rate of perhaps 72 kilometers per second per megaparsec. And that starts to give us a universe that's like 11 billion years old. And that is younger than the globular clusters, which is problematic, which is where we start going, oh, expletive, what is wrong with the stars? And what's amazing is stars are not a solved problem. So we recently figured out a breakthrough with white dwarfs of, oh, wait, we need to take into consideration how their structure treats energy differently because they're crystalline in nature. And so crystals are going to radiate heat differently, go through phase transitions. The phase transitions take up energy, and that changes the cooling models.
So in theory, you find the oldest possible white dwarf, you know how long it takes you to cool down, and so that tells you when that white dwarf probably formed, and you are going to be within a few, tens of millions of years of when the
Yeah.
universe itself formed, except that figuring out how a star's mass of crystalline carbon, the largest diamond ever, takes to cool down, and all of the different layers and all the different stuff that's going on there, turned out to be a little more complicated than anyone was expecting. Or they
Yeah.
were all expecting it to be incredibly complicated, and nature was happy to oblige.
Yeah. And so what we end up with is when you look at stars, when you look at globular clusters, when you look at white dwarf cooling models, when you look at all these different things, you end up with the universe must be older than 12.9 billion years. When you look at Planck data, you end up with a universe. And when you also look at, when you look at the gravitational lensing of galaxies, you end up with the universe is like 11 something billion years. And all these different ages mean that we're doing something fundamentally wrong. And we don't know what.
Right. Right. And so then again, as it sort of relates to the question that I asked in the last episode, right?
Yeah.
What could it probably be? Because again, up until about 2 years ago, we said with confidence that the universe is 13.8 billion years old. And we said that with confidence thanks to really the Planck data and
Yes.
the most accurate possible measurements of the background temperature of the universe. And as I said, that tells you, you calculate the redshift, and that tells you how long it's been expanding for. So why has this been thrown into dispute now? Why are we no longer saying it's this precise number? What other measurement of the age of the universe has become so accurate to make it now confusing?
It's really doing that mathematical working backwards of, if the expansion rate of the universe is this, then the universe was size 0 at this time. And so we're getting 13.8 from Planck. That hasn't changed. When we look at the geometry of space using gravitational lensing to see different paths of light through the universe from distant quasars, that is consistent with a much shorter length of time for the universe to have been around, under 12 billion years old. And that's also where we're getting from the expansion rate that's measured from supernovae. And it all comes down to this stupid expansion rate.
Right.
Who do you believe?
Right. And if you could, and since measuring the ages of stars in globular clusters and measuring white dwarfs is complicated, possibly too complicated for us to get a really accurate number that we can feel really confident about, we have to rely on these other methods. And the problem is that, I mean, literally the last episode that we did really covers this, that now the measurements of the expansion today and the dark matter distribution back at the beginning of time are both accurate enough to be certain that they're the right answer, but they don't match.
And so the question becomes, where all multiple places do we have bugs in our model of the universe?
Right.
And this is usually a matter of everything is more complicated than we thought. We aren't always creative enough to figure out what the universe is doing. And so we're in a position of, well, we only just figured out hints of the complexity of white dwarf cooling models. It's not just thermodynamics as I learned to treat it when I was an undergrad, first learning this stuff. The physics coming out of the Planck models, where we're looking at the lambda cold dark matter models of the universe, Well, if the temperature structure was fuzzy with different pockets of different temperatures, that could change everything. It's the details.
And so, and I know you don't want to talk about spacecraft that haven't launched yet.
That's all right. That's all
but
right.
but
Yeah.
there is a telescope, a super space telescope that has just been packed up nice and tight and is being sent to its launch site in South America that could help us finally answer this question, right?
So are you talking about the it shall not be named space
I'm
telescope?
saying the word. I'm saying the James Webb Space Telescope, due for launch in March 2021. That's the one I'm talking about.
So it will help.
Yeah. But you know, we mentioned like there's some brand new cutting edge thinking about just like that dark matter could have been fuzzy and that could provide the reason.
Yeah. And I think we're going to need more than just observational breakthroughs. You can look at things all you want, but the problem is we can't see inside them. So we need breakthroughs in thinking and understanding stellar evolution. We need breakthroughs in thinking in understanding lambda cold dark matter, or maybe lambda modified cold dark matter. We need breakthroughs in thinking that allow us to either accept or deny that type 1a supernovae are consistent in luminosity across the age of the universe. And all of these different things are going to require new technological breakthroughs beyond what JWST represents. They require new models, new ways of looking at the physics. We have no idea what dark energy is. And JWST isn't going to solve that, at least as far as we know.
Right, but JWST is going to be able to look right out to the edge of the observable universe and watch as those first galaxies are coming together. And my understanding is that the way dark matter behaves will have an effect in the way when it was dominant early on, and it was, you know, it was affecting the way these galaxies were coming together. That might help provide one, you know, more insight into whether dark matter is cold, whether it's warm, whether it's fuzzy, whether, you know, like it will confirm various models of dark matter and throw other ones out the door.
I think that will happen. I think it will also cause a great deal of confusion initially, because we're going to need new creative theories. We're already starting to find results that we can get from ground-based systems looking at the most distant forming clusters of galaxies. These are systems that formed just a few 100 million years after our universe came into being. And galaxies are already forming and going gangbusters in massive structures, which is something we hadn't really understood could be a possibility until recently. So we need those theoretical breakthroughs as well. And James Webb is going to be out there going, nope, you're wrong on this, you're wrong on this, you're wrong on this.
Yeah. But right now there isn't a gadget that can do that.
Not as easily as JWST can do it.
Yeah.
I have to admit, I am so impressed with the science that they are pushing to get from ground-based instrumentation. And the big difference between what JWST is going to be able to do and what these ground-based systems are able to do is our stupid atmosphere blocks infrared light in many wavelengths. And so while we can do some infrared work from the planet's surface, we can't do everything we'd like to do because the atmosphere gets in the way. And where JWST is going to shine is catching these colors of light that are ultraviolet stars that have had their light redshifted all the way into the colors that we can't detect from the surface of our planet. So right now we do the best we can. And I really think we need to give props to the people who are figuring out how to do the science that JWST was supposed to do, supporting missions like TESS. And they're doing it now in this gap before we have JWST. So basically, I just want to say hands off to people running the mega Earth-based telescopes. You guys keep surprising me, and it's awesome.
Oh yeah, yeah. It's pretty incredible. And when the next generation come online, they're not.
Oh, yeah.
It's not going to be long.
No.
You know, we've got
LSST is under construction.
2021, the Extremely Large Telescope. Yeah, in 2026, the 30-meter telescope is sort of, you know, to be announced.
Yeah.
Whether it ends up in Hawaii or whether it moves to the Canary Islands, and of course the Magellan Telescope comes first, 2024. So it is not long for a revolution of just astronomy in general, and they will be used. So I guess, which observation or which experiment do you think is going to allow us to then say again with some level of precision how old the universe is?
At this point, I don't think I'm creative enough to make that kind of a prediction. I really think we need some fundamental change in how we understand what drove inflation, what is driving the expansion today, what is dark energy. If we can figure out what the heck dark energy is, I think a lot of other things are going to fall into place. But I don't know if that answer is going to come from particle physics,
Right.
come from observational cosmology. And so it could be that it comes to us from CERN, or it could be that it comes to us from a telescope, and I don't know which.
Yeah. So someone's going to figure out how to really accurately measure the age of cooling white dwarf stars. Someone's going to figure out how to really
Yes.
accurately measure the age of globular clusters. Somebody is going to figure out how to track the changing expansion rate of the universe, or somebody's going to figure out how to really accurately measure or predict what the right form of dark matter should do to explain the what we see in the cosmic microwave background radiation. And one of those is going to give us is going to be the one that astronomers are going to mostly agree on, and that one will give us the most accurate measurement of the age of the universe that we can hope for now.
And until then, we have from the Planck collaboration an expansion rate of roughly 67 kilometers per second per megaparsec, and a 13.8 billion-ish year old universe. And from everything else, we're looking at, well, a greater than 70 kilometer per second expansion rate to the universe, and a universe younger than some of the stars.
There we go. Enjoy. As always, right? We are in the middle of these discoveries. And if this feels frustrating to you, then you have no sense of adventure.
It's true.
It's fun to watch the discoveries pile up, to see the conversations go on, and just enjoy the journey. Stop being so impatient. This is fun.
This is why we science, because we don't know everything.
Because we don't know, yeah. All right, Pamela, have you got some names for this week?
I do. I would like to thank Brett Peterman, Jason Graham, Bart Flaherty, Kenneth Ryan, Russell Petto, Martin Dawson, Paul Wheeler, Dan Letman, Glenn McDavid, Dean, Shannon Humber, Dwayne Isaac, Kristen Brooks, Ryan James, Skiela Penflico, Eric Feringer, Darkle Daniels, Rachel Fry, Gregory W. Joyner, Brandon Wolverton, Ron Thorson, and Matthias Hayden.
Thank you, everyone. And Pamela, we'll see you next week.
Sounds great, Fraser.
All right. Got to stop and save. And are you done? You got to run?
I can answer maybe one or two questions.
Sure. Arjun asks, since gravitational wave observatories will see gravitational waves from the early universe, won't the distance to the events be in the models the scientists use to determine what caused the waves? So if we see primordial gravitational waves in all directions,
I don't think we have anything planned that can do that except for maybe Lisa.
After Lisa comes the Big Bang Observatory,
Okay.
and that's going to be the one that'll do that. But it's not
Yeah.
due for the 2030s, maybe even the 2040s.
Yeah.
It's going to be essentially 12 Lisas.
I'm hoping we can solve this before then, I think is my answer.
Right. I mean, it's going to be a wondrous gadget anyway, because it will allow us to see a time that we can't see with regular light. You can't see through the cosmic microwave background radiation, but you can see through it with gravitational waves. So
yeah, and this is one of those things where my entire early career I was like, we can't know anything from before the CMB.
yeah,
But it turns out maybe we can.
yeah, that'll be amazing. All right, next question. We'll do these like really quick. Let's see.
Oh, tomorrow night I am giving an International Observe the Moon Night talk at the Flandreau Science Center here in Tucson, Arizona at 7 p.m. Pacific time. And we will be trying to live stream that on twitch.tv/CosmoQuest.
Makopa asks, how are we sure that the cosmic microwave background isn't just the Milky Way's inner glow?
No.
You would see structures in the cosmic microwave background that perfectly match the shape of the Milky Way, and we don't.
And more than that, distant galaxies, their gravity shifts the light of background photons that are coming to us from the cosmic microwave background. This is the Zhenev's-Yeldovich effect.
Right.
And because we see the light of the cosmic microwave background getting affected by intervening objects, we know the light has to come from behind those intervening objects.
There you go. Scientists thought of that.
And I just like to say Zhenev's-Yeldovich effect.
Yeah, exactly. All right. You know what? I'm going to let you go. I'm going to wrap this up. So thanks, Pamela. Thanks, everyone, for watching us today. Thanks, as always, to all the moderators, all of our friends. If you want to be part of the community, go to wshcrew.space. That's where this chat comes from. And these 2 episodes will show up on the feed over the next couple of weeks. I've got an interview with Ron Garan on Monday, astronaut Ron Garan on Monday over on my channel. So if you want to talk to an astronaut, this is your chance. Ask him all those questions that you've got about astronautry. So, all right.
Sounds great.
All right. We'll see you later, everybody. Thanks.
Bye-bye.